Okay, so now we'll study about second order reactions. Similar to the previous reaction, we'll consider here a decomposition reaction in which A, the reactant, undergoes decomposition to give products. But the rate law here will be different. In this case, the rate of the reaction, that is d epsilon by v dt, will be directly proportional to the square of the concentration, because this is an example of second order reaction. So we can write it in the form minus dc dt equal to kc square, as we have previously proved that d epsilon by v dt is equal to minus dc dt. Now if we integrate both the sides, from the concentration term will be integrated from C0 to C, and the time term will be integrated from 0 to t. As we know that at initial time t is equal to 0, the concentration's value is equal to C0, so we get this, and which ends up to this 1 by C minus 1 by C0 is equal to kT. This is the integrated rate law of second order reaction, right? So now if we plot 1 by C with respect to t in a graph, 1 by C with respect to t, then we'll get a straight line in which the intercept's value will be 1 by C0 and the value of slope will be k. K will be the slope. Okay, so now similarly for second order reaction also we can calculate half-life like the one we calculated in first order reaction. We know that for half-life at t equal to t half, the concentration becomes half of the initial concentration. Now putting these values in the above equation, that is 1 by C equal to 1 by C0 plus KT, we will get the value of t half will be equal to 1 by K into C0. So in this case we see that t half is inversely proportional to the initial concentration of the reactant. This is very important for exam purposes, because supposedly we are said that the half-life of a reaction is inversely proportional to the initial concentration of the reactant, and from here what information can we get about the order of the reaction? Then we can say that as the t half is inversely proportional to C0, so it is a second order reaction. Now we have seen second order reaction considering a reaction of only one reactant, that is a decomposition reaction. Now it can also be that the second order reaction takes place by multiple reactants, that is two reactants are reacting to give the final product. In this case the coefficients have negative sign because they are reactants. We know that for the case of reactants we use negative sign as coefficients. The rate law can be written as follows, that is d epsilon by v dt is equal to rate constant multiplied by concentration of A multiplied by concentration of B. But we also know that the rate of the reaction can be written as this 1 by mu A into dCA dt and 1 by mu B into dCB dt. So they can be written as follows, that 1 by mu A into dCA dt is equal to K Ca into Cb, and similar is the case for reactant B. We also know that Ca is equal to Ca0 plus mu A into epsilon by V, and Cb equal to Cb0 plus mu B into epsilon by V. So we write that d epsilon by V dt equal to, this comes from here, this equation, d epsilon by V dt is equal to K into Ca into Cb. Now the value of Ca and Cb comes from this equation and this equation, so we substitute it over here and here. So we get d epsilon by V dt equal to K into Ca0 plus mu A into epsilon by V multiplied by Cb0 plus mu B into epsilon by V. Next what we do is we multiply the numerator and denominator with minus mu A into minus mu B. This will give us this expression, and as it has become a very large equation, so we'll substitute some terms with smaller terms. Say CA0 by minus mu A has been replaced with YA0, C0B by minus mu B is equal to Y0B, and epsilon by V equal to Y. We replace it in the following equation in the above equation, and we get this expression, which comes down as follows, that dy by y0a minus y into yb0 minus y equal to mu a into mu b into k dt. Now considering the following two cases, the two cases can arise in which ya0 equal to yb0, and the other case is where ya0 is not equal to yb0. This is the second case. So in this case, ya0 equal to yb0, the substances A and B are present in the required stoichiometric ratio, that is the same ratio they are present. So as ya0 equal to yb0 in this case, the term yb0 minus y will also become ya0 minus y, and so it will become dy by ya0 minus y whole square integrated from concentration of 0 to y, and the t term will be integrated from 0 to t. So after integration we will get, so after after integration we'll get this 1 by ya0 minus y minus 1 by ya0 is equal to mu a into mu b to kt. Okay. Similarly we'll get for the reactant B also. If we consider that ya0 equal to yb0, both these equations are correct. Okay, so it can be written that 1 by Ca minus 1 by Ca0 is equal to, we'll replace the terms that we have previously substituted, and we'll get this following equation for reactant A and this reaction equation for reactant B. Now considering case 2, which is more interesting, is when the two ratios are not in stoichiometric ratios. The stoichiometric ratio has not been conserved. So in this case the integration takes from 0 to y again in both the terms, and the dt term is integrated from 0 to t. We get ln ya0 minus y by ya0 and ln yb0 minus y by y0b, which is equal to minus mu a into mu b k yb0 minus ya0 into t. In the last we get this final expression. Now if we consider that B is present at great excess, any reactant, we have two reactants, let's consider one of the reactant is present at a very large extent than others, because usually in reactions, suppose a reactant reacts with another molecule, suppose we consider that to be H2O, and that gives products. Now usually in reactions H2O is present in bulk amount, so it remains unchanged even after the reaction has finished. So we can consider that B is present in so much amount that B's concentration doesn't change over time. So yb0 minus ya0 can be considered as y0b, because B is present at great excess, so yb0 is much greater than y0a. And so Cb by Cb0 is almost close to 1, because the final concentration and the initial concentration remains same. So we can write that ln Ca by Ca0 is equal to minus into minus mu a Kcb0 into T. From this equation we get that. We have replaced the term Cb by Cb0 equal to 1, and so ln 1 is equal to 0. This becomes 0, and so ln Ca by Ca0 equal to minus bracket minus mu a k Cb0 into T. Similarly for the case of reactant B, if the reactant A is in large amount, then the equation will be in terms of B. So these are effectively first order reactions equations, because consider this equation, ln CB0 equal to mu B K CA0 T, right? So this can be written as CB is equal to CB0 e to the power minus mu B K CA0 T. This is actually the integrated rate equation of a first order reaction. Hence we can call it as this, that if one reactant is present in excess amount, the rate law or the integrated rate equation becomes such that it shows that only a single reactant is present and the other is not present, although it is present. So these type of reactions are called pseudo first order reactions. We call them pseudo first order reaction because although they are second order reactions, they act as first order reactions. Okay, this happens when one reactant is present in much larger amount than the other. So this brings us to the end of this video. We'll continue on higher order reactions and the application of order of reactions in the later video. Thank you.